Nuclear reaction. The two general kinds of nuclear reactions are nuclear decay reactions and nuclear transmutation reactions. So nuclear decay reaction, as we have already discussed earlier, is also called radioactive decay. So an unstable nucleus emits radiation and is transformed into the nucleus of one or more other elements. The resulting daughter nuclei have a lower mass and are lower in energy, so more stable, than the parent nucleus that decay. Nuclear transmutation reaction is a nucleus reacts with a subatomic particles or another nucleus to form a product nucleus that is more massive than the starting material. As we shall see, nuclear decay reactions occurs spontaneously under all conditions, but nuclear transmutation reactions occur only under very special conditions, such as the collision of a beam of highly energetic particles with a target nucleus, or in the interior of stars. We begin this section by considering the different classes of radioactive nuclei along with their characteristics, nuclear decay reactions, and the radiation they emit. So note, nuclear decay reactions occurs spontaneously under all conditions, whereas nuclear transmutation reactions are induced. So here are the classes of radioactive nuclei. We have neutron-rich nuclei. The nuclei of the upper left side of the band of stable nuclei have a neutron-to-proton ratio that is too high to keep a stable nucleus. So these nuclei decay by a process that converts a neutrons to a protons, thereby decreasing the neutron-to-proton ratio. Second, we have neutron-poor nuclei. Nuclei on the lower right side of the band of stable nuclei have a neutron-to-proton ratio that is too low to keep a stable nucleus. So these nuclei decay by a process that have the net effect of converting a proton to a neutron, thereby increasing the neutron-to-proton ratio. And lastly, heavy nuclei with a very few exceptions. Heavy nuclei, those with atomic mass, a mass number of greater or less than 200, are intrinsically unstable regardless of the neutron-to-proton ratio. And all nuclei with atomic mass of 83 are unstable. This is presumably due to the cumulative effects of electrostatic repulsion between the large number of positively charged protons, which cannot be totally overcome by a strong nuclear force, regardless of the number of neutrons present. So such nuclei tend to decay by emitting an alpha particle or a helium nucleus, which decrease the number of protons and neutrons in the original nucleus by 2. So because of the neutron-to-proton ratio in an alpha particle is 1, the net result of alpha emission is an increase in the neutron-to-proton ratio. So important to take note that nuclear decay reactions always produce daughter nuclei that have a more favorable neutron-to-proton ratio, and hence are more stable than the parent nucleus.